I'm a PhD student at Stanford, working on the intersection of machine learning and systems. In today's talk, I just want to talk about kind of some of these new machine learning architectures that are starting to pop up, that some of which you may have heard of, that are starting to potentially emerge as alternatives to transformers. And I want to talk about kind of one piece of the methodology in developing these models that doesn't get as much attention. Like we focus a lot on the specifics of the architecture and the perplexity and this and that. But I want to actually focus on one little bit that you see pop up in all the papers around these new architectures, and that, in my opinion, is probably one of the more important insights that we've come across in the last few years, and kind of how we've been able to make all this progress. So, and this is what I like to call the unreasonable power of synthetics when you're trying to develop some of these new models. The kind of the motivation for this talk is over the past 6 months to I guess 6 to 7 months now, we've seen an explosion of sort of new architectures in machine learning. If you're familiar with Mamba, these state spaces, Mamba 2, these selective state space models have started to emerge as potentially a challenger to transformers. DeepMind released these models called Hawk and Griffin in February. I think that combines some recurrent neural network ideas with some local attention ideas, some new architectures that can scale better than transformers. A few months ago, some of my lab mates at Stanford released this model called Based, which shows that linear attention can actually be a pretty convincing alternative to the full quadratic self-attention. What's remarkable is, all these about 6 years ago, after kind of 6 years, it might be the case that finally the transformer dominant paradigm may be coming to an end. And in today's talk, I'm not going to focus so much on any of those particular artifacts, but rather on kind of the common trends and research methodologies underlying a lot of these models. In other words, if you look at this graph, so on the x-axis, you have time, on the y-axis, you have perplexity. Over the past just 6 months to less than half a year, we've actually made quite a bit of progress. So kind of the really interesting question is, how did performance of these new architectures, these new models improve this fast? And I'll argue that the answer has to do with a really simple idea of studying simple synthetic languages to try to understand what is, the core expressive power of some of these architectures. And I'll kind of argue that the key insight behind a lot of these new ideas, these new machine learning models come from deep understanding of some really simple synthetic languages. You can almost think of them as simple toy examples. And hopefully, as you leave this talk today, if you're interested in understanding these models more deeply, if you want to actually maybe develop some new architectures for some problem that you care about, I'll urge you to try on some of these same approaches, kind of using this deep connection of domain knowledge and using simple synthetics to try to understand some really complex learning problems, like for example, language modeling and understanding. This talk will roughly be split into 3 parts. Most of it will be in the middle. But first, we're going to turn the clock back to 2021 and remind ourselves of the state of the world a few years ago before the explosion of all these new architectures. So back in 2021, transformers were starting to show their promise on language modeling. You were starting to see all these papers that were like, what's special about transformers? How come they can learn these things that other things can? Does it just scale? Is it just this? Are transformers Turing complete or whatever? And so we'll turn the clock back to 2021 and start to see, why is it that people thought there was something special to transformers? It turns out actually there was a gap between transformers and the other efficient architectures that we had at the time. Then we'll see how we started to use a really simple synthetic called associative recall to try to start to close that performance gap between transformers and some of their more efficient alternatives. And then in the last part of the talk, we'll briefly talk about how these synthetics have evolved and kind of have started to inform the key architectures, some of those key innovations that you saw at the beginning of this talk. So now let's get started with this first part. So we'll turn the clock back to 2021. This is when we first started getting interested in these subquadratic, more efficient models. So there's this emerging class of primitives called state space models that you can kind of think of as a mix between recurrent neural networks, RNNs, and convolutions. They had some nice computational properties. So from the computational side, the convolution part of that equation means you can train them in n log n time in the sequencing. So if you have a very long sequence, the computer is going to scale in n log n, compared to attention transformers that compute will scale in n squared. So this seemed to be, a pretty promising computational primitive for long sequence. The RNN part was even more enticing. It means during inference time, during generative inference, you can generate tokens at roughly O of 1 on compute and memory costs. So that was very exciting. But they had these nice compute properties, but there was also increasing evidence that they had very strong quality on a lot of sequence modeling tasks, things like speech synthesis straight from audio waveforms. If you're familiar with this startup called Cartesia that just released this new model called Sonic, that it's a very good kind of text-to-speech model that runs very fast and is very good. The first kind of evidence, the first inklings that this was a good idea was starting to appear in 2021. They were showing strong performance on things like time series analysis from brain EEG waveforms. And our question was, there's this new primitive, it seems to be high quality, has this nice subquadratic scaling, does it work for language? I'll also briefly note, it wasn't just state-based models at this time. There's linear attention, kind of approximations to attention. People were really trying to get this more efficient replacement and kind of seeing promising results here and there. The only problem was, if you took any of these methods, I'm going to focus on state-based models in this talk, but it was also true of linear attention back in the day. If you took those replacements for attention and just took a transformer and replaced attention with these methods, you would see a huge quality gap. So here I'm showing you a metric called perplexity, and in this metric, lower is going to be better. And you can see that, so what I've done here is just taken a transformer and replaced the attention with these SSM alternatives. You can see there's about a 5-point gap on perplexity. So 5-point gap, what that means is that's roughly the difference between a 125 million parameter model and a 7 billion parameter model. So what I've done here is I've just asked two models of that size, kind of who is Alan Turing? And you can see that the smaller model is doing this really weird thing where it seems to be hallucinating that Alan Turing is the co-founder of Ethereum, which is a crypto startup. Also the founder of the Newcomer, which is a crypto startup, which I don't know, I don't think that's quite what Alan Turing did, if I remember my history correctly. Whereas the larger model can kind of successfully identify that Alan Turing was this influential mathematician in the 20th century with groundbreaking work in cryptography and computer science. So our goal was, okay, if you do this replacement, you seem to have this huge quality gap. Can we start to understand and close this quality gap? So in 2022 and into early 2023, we turned to this idea of synthetics. The basic idea was, instead of trying to understand the performance of these giant models on this really abstract task of language modeling, can you instead study a much simpler problem and use that to gain insight to the performance of the performance gap? I'll briefly tell you about how our general idea of how we like to approach problems like this. So once we've identified a promising primitive like state-based models, we want to deeply understand the use case. And in this case, that's going to be language modeling, next token prediction. Then instead of just kind of tweaking the primitives a little bit, trying to train a bunch of models, kind of random walk your way to a better alternative, instead we're going to build a really simple synthetic to try to understand what is that performance gap. And then hopefully that synthetic will give us some insight which we'll be able to use to develop some new solutions. So here I'm going to do a deep dive into some older work called H3, Hungry Hippos, but we'll see how we can actually use the insight from our synthetics to start to close the gap in performance to those models. So let's briefly go over language models and kind of how transformers do language modeling. The basic conceit of a transformer is you're going to take some input, split it into a sequence of tokens. For language, that could mean that each word in your sentence could be a different unique token. And what a language model is going to do is it's going to, given some amount of input, try to predict what comes next. So here I've put together a really simple sentence. Barack and Michelle Obama went to Harvard to visit their daughter. And the hope is that the model will have seen enough data during pre-training time to know that the Obamas have two daughters. One of them went to Harvard and her first name is Malia. So you can try to predict that the next token is going to be Malia. The way that attention does this is it tries to compare every token in the input to every other token. So you can, I've just gone ahead and put this together in a simple visualization here. Each orange token that's generated, you need to do a dot product comparison with each of those blue tokens that comes before. So the way that transformers do this is that they compare every token to every other token. So this is where you get that quadratic compute. You can imagine as these vectors get very, very long, this is going to take increasingly more compute. But the reason why it's helpful is that when you're trying to predict this next word, it's really useful to be able to go back and look at some of the words in your sentence, like Barack, Michelle Obama, Harvard daughter, put those context clues together to predict what is the word that comes next. Okay, so how can we capture this basic pattern, this basic insight in a really simple synthetic problem? We put together a couple to try to do this. And one that was particularly helpful for us was this one called associative recall. So this is a really, really simple synthetic language. You can imagine there's, let's say, 20 tokens. It's kind of a key value lookup problem. Half the tokens are going to be keys like A, B, C, and D. The other half of the tokens are going to be values like 1, 2, 3, and 4. It's a really simple task. In each sentence, you have a unique mapping from keys to values, like I've shown here. And the task is really simple. Just at the end of the sentence, you have some key that doesn't have a value, and you just need to go back and look up what is the correct value associated with that key. This is a really simple task. You can probably solve it with, say, 5 lines of Python code and a hash table. But what's really interesting about this problem is that it just mimics this one key aspect of language. So it doesn't mimic all of language at all, but it mimics this one key aspect, which is just the ability to recall information from earlier in the sentence, which like I said earlier, is just useful to try to do that next token prediction. The other thing that was really interesting about this task was that SSMs, the state space model, showed a large gap to transformers on the simple task. So here I'm showing you the accuracy of that last token prediction, showing you the performance of some really simple 2-layer model. So a 2-layer transformer compared to 2 SSM models where we just replace that attention model with these SSMs. So you can see that the transformer can perfectly solve the task, but these SSMs really struggle. How is it the case that you have this really simple task that I can solve in 5 lines of code that these SSMs, that these super powerful sequence models somehow can't be able to solve them? So what we did was we actually, given this really simple task, we sat down. And one of the nice things about such a simple task is you can actually completely understand what the models are doing. So we literally sat down and tried to manually write out weights by hand. Like instead of trying to learn those weights with SVD, we just wrote them out by hand to try to convince ourselves, why is it the case that these SSMs are really struggling? And I'll walk you through kind of what we did and the insight that we came when we did that. So here I'm showing you a visualization of what it might look like to write out weights. So I'm showing you kind of a signal processing view of these SSMs. In this first row in this, let's see if you can see my mouse. For this orange curve, you can think of this as the embedding of your model. So I've just gone ahead and assigned a unique real value to each token in the embedding space. And I've just assigned a very sharp negative value to this one token because it's ultimately going to be our answer. We want to just be able to very visually pick out if we got the right answer. Then what we did is we wrote out a set of SSM weights. So here we just wrote out the weights by hand. You can think of each SSM as a convolution. So you can think of this blue curve as just a convolution curve. It's a very simple kernel. Mostly it's 0, but you just have this one spike here. Oh, and sorry. So what that spike means is basically it's just a very, very simple kernel. But what's important about this is when you take this orange curve and convolve it with this blue curve, you actually get this green curve. And critically, at the end, you can see that you get this very sharp negative value here, which exactly matches up to this orange value here. So what that means is that for this particular example, for this particular token, we are actually doing the next token prediction correctly. The SSMs actually can go back and pick out the right token. But the only challenge is we have now encoded this particular blue curve, this particular filter into the weights. So what that means is if I just go and sort of flip around the order of some of the tokens that are input and then run our system forward, so we should still get the same answer. If you now run the exact same system forward, we're now going to, in fact, get the wrong answer. So you can see that this green dot at the bottom no longer matches that very sharp negative dot for the orange. What's going on here is that we hard-coded in this convolution filter into our SSM, and we are now looking up the wrong token. So the intuition is that these SSMs are very good at doing a static lookup. So you can do something like pick out the token that came 5 tokens or 10 tokens before me. But it's very difficult for them to do a dynamic lookup based on the last token. And in this particular synthetic, you don't know how far the gaps between those C's are. So you can't just hard code a particular static lookup table. But now we have a fairly, well-defined technical challenge of how can you get this family of SSMs to do a dynamic recall based on the previous tokens? So I'll just walk through kind of the simplest possible change that we made to these SSMs to try to get them to do this. And the simplest fix that we thought of was this really simple idea just called element-wise gating. So the way to think of this is each of these circles with dots in them, you can just think of these as point-wise multiplication between two vectors. And what that's going to allow us to do is it's going to allow us to pick out different pieces of kind of unique information from our input and then kind of compose those into more complex logical statements. So I'll walk you through, again, a set of ways that we can use to solve this problem. First, I'll point out that we are going to, in fact, get the right answer here. At the end of all this, that green dot is going to match up to this orange dot. We're going to do it in a slightly different way than the previous slides. So in this first token, again, we're just going to pass forward that exact same embedding of the current token. So this orange curve is the exact same one that you saw a couple slides ago. In this second branch of the model, we're going to do something different. And we're just going to put together a really simple indicator function of whether that previous token is that C key. So you can see there's this orange spike here because the previous token in the previous time step was this C. The interesting about this is when you take this orange curve up top and multiply it with this other orange curve, you're going to get this purple curve. And what we've managed to do here is we've managed to extract the embedding of that one token. So now we have this third curve that is just has this one negative spike here corresponding to the embedding of one token. For the SSM weights, we're going to do an even simpler filter than we had before. We're just going to have a really simple filter that's just going to be a global memory store, kind of a convolution filter of all ones. What's interesting is you take this purple curve, convolve with this blue curve, and now you've successfully memorized the value of that one embedding for the rest of the sequence. Now in this third branch, we're just going to have another really simple indicator function of whether the current token is the C key. You can see that there's these two spikes here, right, when the C keys appear. But then when you take this purple curve point-wise multiply with this orange curve, you're now going to get this green curve. And in particular, we have successfully returned the value of this one embedding, but only at the end when you see the C key. So that's how we can actually get the right answer. You can take this exact same system and switch around the order of the tokens like we did before, run the same system forward. You're going to see that we still get the right answer. So this system is kind of invariant to some of those shifts, changes in the order of the tokens. You can even change the mapping from keys to values, run the same system forward, and you can still get the right answer. So you can see that green dot now matches up with that other orange dot. The basic intuition here is that these simple gating mechanisms are allowing for some kind of data-dependent selection mechanism. And in fact, we can prove this. So with the vocabulary, if their vocabulary size is S, this simple H3 layer that I've shown you can solve the associative recall problem with parameters that grow linearly with the vocabulary size. And kind of with later improvements, we can get to sublinear scaling in the vocabulary size, kind of by doing a smarter mapping between the tokens in our embedding space and between the tokens in our vocabulary and the embedding space. It's not just that we can solve these in theory by manually writing them out. We can also actually narrow the gap when we actually train up these models. So when you train up a really simple two-layer model like this, you can see that this really simple H3 layer can nearly close the gap to transformers. Okay, so we can solve this really simple synthetic, but does that actually translate to actual language modeling? So what we did is we now took these layers, replaced the attention models, scaled it up to 3 billion parameter size. And here we saw that we could start to match these transformers in upstream training metrics like perplexity. So here lower is better again. So this was 2022, 2023. So we could match the best transformers of the day, the best open source transformers of the day. And we also saw similar stories when we went to do things like zero-shot, few-shot learning on tasks like superglue or glue. That's kind of, some preliminary evidence that this idea of synthetics is a decent idea. But now actually I want to jump forward now to the more recent models, to the ones that have been coming out in the past few months. So, this was a really simple idea that we had like in 2022 that we were able to make a little bit of progress back then, but has this general approach, held water over time. And the really interesting thing is that you're seeing all these new models come out, and their basic way that they make progress is still the same thing. So this Mamba model, if you read that paper, they make a lot of noise about kind of this selection mechanism. You can think about that as just another way of doing that selection that we did in H3, with a slightly more nuanced look at this selection mechanism. So here, the selective copying task is very similar to this associative recall task, but kind of looking at maybe more tokens at the time. This induction head task is a very simple version of the associative recall. And generally, the observation that they make in Mamba is that they create a better selection mechanism. And their observation is, on tasks like perplexity, better selection mechanisms lead to better performance. So as you kind of move down on this perplexity and kind of look at some of these scaling laws, basically, as you move down, you get to better and better selection mechanisms. So you can see there's this hyena, RWKV, which kind of look like H3. There's an H3++ where they tweak the selection a little bit. Then Mamba adds some more selection mechanisms into the actual parameterization of the state space model itself. This Griffin, this Hawk and Griffin work out of Google DeepMind, they also try to tackle this problem, and they also introduce a set of synthetics for copying and retrieval. So the selective copying task, very similar to the associative recall. Induction head's very similar. Then there's also this phone book lookup. And again, they basically go through the same process of, we're going to use the synthetics to try to make the actual architectures better. And the general observation is, if you can improve the retrieval abilities on these copying and retrieval abilities on the synthetics, you can do even better and get even better performance. This work out of Stanford recently called Based. Here, they're again looking at the associative recall task, and their basic insight is that for all of these new subquadratic models, there's this balance you have to do between your performance on an associative recall and the size of your hidden state for the throughput. So you can see here that for attention, we can see it usually does the best on associative recall, because their hidden state grows with the length of the input sequence, whereas all these other subquadratic models have a future dimension that is kind of fixed. And the basic insight of this paper is, if you can design an architecture that can do these synthetics with a better balance between the recall performance and the size of your hidden state, you can actually get better performance. So here, I think that these orange dots are the base model. They basically show new points on the Pareto frontier between the recall and throughput of these models. So you can balance the recall performance with the size of the hidden state. At some point, we got really excited about BERT models for about 6 months, and we were like, okay, how can we take these insights and train up some BERT-style models? And we basically, again, put together this really simple synthetic. We call it a bidirectional associative recall, where basically the answer can come after your query. So you have to not just look backwards in time, but also look forwards in time for your answer. We were able to use these to train up some long context BERT models, these M2 BERT models, and train them up to be these long context retrieval models. And what we generally found was that if you can increase the context length of these retrieval models, you can do much better long context performance than in some cases the much larger models. So here, this tiny dot is an 80 million parameter model. But if you can extend the context length in the right way, you can outperform much larger, shorter context models, in this case, like a Mistral 7B. Kind of take a step back and look at sort of the order of operations and kind of what to take away from that is that the really remarkable thing that happened was, we took this really complex problem called language modeling. We're like, we don't really understand what's happening. There are, the whole field of linguistics is trying to understand human language. What we were able to do in machine learning is we were able to boil just one, little aspect of it down to these really simple synthetics, and then use those synthetics to try to get some insight to how to develop better architectures, better models. And that led ultimately to improvements in quality and efficiency. And then as I kind of come to the end of this talk, I just want to show you some fun little demos of what these models can do today. So this is actually a little bit of an older model now, about a year old. This is a model called Striped Hyena. You can think of it as a scaled up version of H3, so scaled up to 7 billion parameters, and then with some conversation tuning on top. So this was trained by some of my colleagues at Together AI. And this morning I said, hey, I'm giving a talk about AI and machine learning to the Buzz robot community. What's something nice I can say about the community? And they gave me something a little bit generic. It's a pleasure to be speaking to the innovative and passionate Buzz Robot community today. I assume that the community did not exist when this model was being pre-trained. So that a year and a half ago. So that was a fun little thing. I gave another version of this talk at MLSys about a month and a half ago, and there, I was able to put together something a little less generic about MLSys, and it was in person in Santa Clara, so it talks about how Santa Clara is a vibrant and city and whatnot. The other really exciting thing that's happening with some of these models is that there's some evidence that they are kind of useful in other modalities as well. So this is a model called Evo, again, a scaled up version of H3, scaled up to 7 billion parameters, except this time it was pre-trained on DNA sequences. So instead of training them on text, it was trained on DNA. The really exciting thing about this was it wasn't just a good DNA model, it was also a pretty decent model for RNA and proteins as well. So you could take this primitive that we developed for language, and it seems to also be able to generalize at least a little bit to these other modalities. So that's pretty exciting, and potentially points a way forward for some of the things that we can do. So with that, that'll be the end of the talk. And again, thank you so much for having me, and super happy to take some questions now.
You were talking about dynamical recall of different pieces. I'm just wondering, what is the logic behind the dynamic?
I'll give you an example. So if I say the word elephant right now, and then we talk and say some number of words, and I could like give a whole speech and say some random number of words. And then I ask you, what is that word that I said before? You want to still be able to recall that. So what a SSM can do is it can do something like, if I know that I'm going to say the word elephant, and then I'm going to need to use that piece of information in exactly like 125 words or exactly 10 words. And I need that piece of information in exactly 10 words. A SSM by itself is very good at doing that exact lookup. So if it's very important for me to have this word elephant to make some prediction later, and I know it's going to be exactly 10 words from now, it's very good at this. So there's a number of tasks where this is the case, like time series can be very regular. Audio has this property because syllables take about the same amount of time. So it takes about the same amount of time to figure out like how to generate two different sounds. But language does not have the property. It does not have this property because you don't know ahead of time if you say some key piece of information when you're going to need to use it later. So the point of this dynamic selection is just to say, hey, I can dynamically decide when to put a particular piece of information into the hidden state of my model and when to extract it later. So at this point, you can still see you can still see these things happen. Like if I ask you what that word I said earlier was, you can all still think about it and respond to it, even though you don't have to say, oh, I'm only going to remember it if Dan said it exactly 2 seconds ago or something. So that's kind of the intuition behind it and why you want to be able to do this with language. I've seen a claim that some types of emergent and context learning capabilities only occur in transformers. Is there evidence of these new emerging similarly in these newer mechanisms? Yeah, so there's a good deal of evidence. So in the H3, even back in 2022, we were doing these few shot learning tests and stuff where it's kind of like in context learning to try to do it. And with those new architectures, performance improves with higher shot learning in mostly the same way as transformers. I'd say as we have developed better and better models, we've gotten more precise about what that means. So I'd say the state of the art right now is we can definitely match perplexity with all the newer models. And there's some evidence that they do a little bit worse at a task like, let's say you paste in a Wikipedia article and then you ask a very specific question about it. So here the new subquadratic models will do less well than the transformers, but there's a paper I think that is coming out very, very soon that I know one of my lab mates is about to release. So very simple changes. I mean, probably by the time this is online, it's probably available already. So that paper is called Just Read Twice. And so you can go look it up now if it's not online already. And that's a paper by Simran Arora. And it's really simple that like, hey, these new subquadratic models aren't quite as good at doing this thing out of the box, but you can just like repeat your context twice. So if you have like article, question, for the right context length, it's still more efficient than the transformer. But if you just do it twice, then they can do things as well as the transformers. So you may need to prompt it slightly differently, but they're still quite performant. And in that paper, they actually showed a more T5 style model can get the best of both worlds, where it can still be very efficient, but it can also have a really good performance of these model on kind of these in context learning things. So I'd say there's maybe a little bit of gap, but it's very rapidly closing. Like if it's not already solved, like today, it'll be like, I don't know, 3 months or something, and it should be pretty much closed.
Do you think that performance of synthetics in design and architecture is evidence for these models like transformers, working mostly through using the same basic mechanism?
Yes and no. So I'd say the yes part is that it's really remarkable that like we close this 5-point gap by like doing one thing better. I think that's strong evidence that like the attention mechanism of the transformer is really only kind of moving the data around based on the input. I will say like some of the more recent work to close some of the other gaps, the synthetics have gotten progressively more complex. So I didn't talk about this as much, but like, so there are some different synthetics that I've seen recently, and you're seeing new synthetics try to capture like different gaps in performance. So a lot of it is captured by this really simple synthetic. There's maybe a couple other synthetics. The no part of my answer is that there's a whole other part of the transformer, which is called these NLP layers, like where all the parameters are. And there we have very little understanding of what's happening. Like we maybe have some circumstantial evidence that they're not super optimal, like they're super sparse. These mixture of experts models seem to be doing well, where like you basically took this NLP and like split it up and like it kind of still works. So there, I think that part of the models, we really don't understand what they're doing very well. We'll come to some deeper understanding soon. The same way that like 2 or 3 years ago, people were saying, oh, transformers are magic, they can do everything. Right now, the state of knowledge is like, okay, these parameters are magic, they're kind of doing everything, but maybe with better understanding, we'll have a better solution.
But I'm wondering potentially what are the like significant advantages of synthetics compared to transformers?
Do you mean the new architectures or?
Yeah. So the proposed new architecture, what they could potentially do better than transformers do?
Yeah, so there's entire modalities where they just perform way better. So audio, images to some extent, time series, like so any of these any modality that kind of looks continuous, they're probably gonna guaranteed be better than transformers, but that's been true of like 2 or 3 years for now. The major advantage in things like text where transformers are doing well already is they're a lot more efficient. So they scale
computationally, right?
Computationally more efficient. So you can train them for longer sequences more efficiently. Inference, if you put in the end, so there's a ton of engineering effort going to making transformers efficient. If you applied a similar amount of engineering effort to these state-based models, they would probably be there. They just have fundamentally less compute, so they would be fundamentally more efficient.
I'm curious about the advantages attention-based models might still hold over state-based models. Should we consider completely replacing attention-based models, or do they still offer significant benefits?
Theoretically, there is still something you get from being fully quadratic. So for example, if you wanted to do something like have a transformer decrypt a hash or something, you would need that full quadratic logic to do that. I don't think anybody's trying to do that with transformers, but I can guarantee you that the state space model would not be able to do it. Or like the number of layers would have to like grow with the sequence of the size of the sequencer or something ridiculous like that. So there are some toy examples you can come up with that like, okay, obviously the transformer is going to do better. Practically speaking, I think the main staying power that transformers have right now is there's a lot more infrastructure around them. We understand how to train them a lot better. There's a lot more like folk knowledge about how to train them. there's a lot more, kind of inference infrastructure around them. So every major company has a really efficient inference stack for transformers because they've had engineers like working on it for ages. But there's maybe like one company or one or two companies that has an efficient inference stack for a state space model. And that's just a lot of engineering effort that you need to put in to kind of have them match each other. Like if a company decided to put that engineering effort in, I'm sure it would do great. But it's just a cost you have to pay, kind of realistically from the business side. And you have to ask questions like, is the long context worth it? Like, are the queries that I'm serving mostly short, like who is Al Gore or something, or is it something where you actually need that long context? So, moving from the academic, this is a really interesting problem for its own sake, to something that it actually has like business value. There's always questions around those, but modulo those kind of real world concerns, they're pretty at par these days for things like language.
From engineering perspective, it will cost to companies to sort of rearrange their stack to the new architectures.
Yeah.
Is it possible to estimate how much that would cost, or like how much time?
If you have really good, so here's the thing. If you have a small team of really good engineers, like 3 or 4 like really top-notch systems engineers, like people who know the machine learning and the systems, you could probably get this down to like on par with transformers in like 6 months. The only problem is there aren't a lot of really good systems engineers on the market who are not already like doing something else that's like critical for a company. So like if you have those people, you probably have them doing the thing that will most directly make the company money today. I mean, one, those engineers are probably very expensive to hire, but also like you have to think about the lost potential income from like not doing the thing that is most pressing right now. Decisions like this are way beyond my pay grade, but you can try to estimate, like, if we freeze the transformer stack for another 6 months, what does that mean for the business, and then is it worth it to like switch up these new things and all that. So yeah, that's just like a business consumer preference type of thing.
Or new architecture should bring like order of magnitude improvement in performance, right? To incentivize them business-wise to make those changes. If it's like a
so for long context,
change,
it's
then
there.
It doesn't make sense, right?
Yeah. So for like long context applications, that's definitely there. But like then the question is like, do you have long context business cases? And historically, transformers have been very expensive for long context. Like we've only seen long context models in like the past 6 months or so. So like, do the use cases exist? I don't know. Like maybe we just all ask Google to spend however many millions of dollars doing it the inefficient way to try to see, is some use case going to pop up that can now justify everybody else kind of jumping on it. Should we expect the cost of attention to drop to O of n? These models are now O of n log n array. So the latest models are kind of O of n. It depends sort of, the latest battleground is kind of the size of the hidden state. So the efficient models now are O of n times d, where d is a fixed number, and you make d bigger, performance improves. You make d smaller, it goes faster. So that's kind of that trade-off. But by some measurements, we're already at O of n. And the general consensus now, I think, is depending on where you dial that d, you get more or less performance. And then there was another question: do you expect the algorithm's efficiency of architecture to keep progressing at the same pace as observed in the last few years, or do you expect that progress may slow down? I think on the context length front, we're probably seeing a slowdown right now, where we're gonna match or maybe exceed transformers. Like maybe there will be this little like wibbling where like transformers we get a little bit better, the SSMs we get a little bit better. Like maybe they'll chase each other a little bit, but since we've more or less closed the gap now, like I wouldn't expect like a giant jump in performance, just from the sequencing bit. I would expect from things like mixture of experts or like doing different things with the MLP layers there. I think we're just at the beginning of that trend. So we may see a giant leap in performance taking these same ideas and applying them to other pieces. But just in the context length, just subquadratic models, maybe not. We'll see.
Is it something that you're sort of working now? Like, I'm just wondering, what is the next steps in this research that you're focusing?
Yeah, so for me, I'm starting to look more broadly at places where like other bigger gains to be made. So a little bit on the architecture side, a little bit looking at those MLPs. The other thing I'm looking at is like with the new modalities that are coming out, like you're starting to see some video generation models, but they're like ridiculously expensive to run. So I feel like there's a lot of headroom there, where we don't really know what is the right thing to do for a video generation model. If we don't know if it's supposed to be autoregressive or diffusion or this or that. So it feels like there's a lot more exploration to do. There might be some new paradigms that start to emerge. Like there's starting to be an appetite to like replace the autoregressive LLMs, like with maybe T5 style or text diffusion models or this or that. So maybe there will be a whole new paradigm that gives us actually an order of magnitude improvement. But yeah, that's kind of where I'm starting to look around as well now.
What is an example of the largest models that have been trained using these techniques?
I think the biggest public one is called Jamba. It's from AI2. I think they basically combine all the techniques together. So they use some Mamba, they use some attention, they use some mixture of experts, put them all together, trained a really big model, and it performs well. It was basically the conclusion. There may be like private models that are trained in like the big labs that we don't know about. But yeah, I think that's the biggest public one that I'm aware of. And it's like many Bs, like many billions is, I believe, the size of it.
Is it like cheaper to train these models compared to?
Yeah, I think for long context, it's cheaper. Yeah, I think that they're able to. If I remember correctly, actually, I don't remember the details now, but basically, if you want to train a long context model, it's cheaper to use these techniques.
Lonnie is asking, with the state space approaches with images, could a 2D convolution work better than linearizing image patches in a vision transformer style?
Yeah, so that's a great question. I think the evidence so far is that they all work about the same, which is kind of remarkable. So you can flatten out your image completely, do a 1D convolution for the whole thing. And somebody actually trained a diffusion model doing this using SSMs, and it worked well. You could do the 2D, you could do the patching vision transformer, and it works well. You can also do the 2D convolution. So you can do the small 2D convolutions like resonance style, or you can do a really big 2D convolution, also works well. It seems like for images, you can do almost anything as long as you have some filter that covers the whole image. It will kind of learn the right thing, which is kind of wild that it works. Maybe why the images deep learning hit vision before language.
Yeah, if I could add to that, actually, just recently there was this ARC prize that was announced, and they had a whole bunch of these tasks, a lot of them vision oriented, that these models seem to completely fail on, even though they look deadly obvious. And it seems like a failure of attention. And I thought it might be kind of very closely connected to the linearizing of patches, which is why I was kind of curious about that. So
I think that could be. I'm somewhat familiar with the ARC prize. I haven't like done the challenge myself, but I know one of my lab mates did it, and then it said you're an AI, not a human. So that was a little embarrassing for him. But I think that was it's really interesting to try to understand what are the failure modes of the current models as well, and what can we do better.
So I see Pradeep is asking for audio processing, what inputs are good for transformers or recent architecture? Is it self-supervised learning based on embeddings, raw audio, or spectrogram?
I actually don't know the answer to this. So I believe that the state-of-the-art audio models are closed source and behind company walls. So I know it has something to do with the state-based model, but the actual way that they process it, is it raw waveforms or some learned embeddings? I'm actually not super sure. In the academic literature, I believe the best thing to do was still to take a model, process some like featureization of the audio, and then go off of that. But that work came out like 2 years ago, so I'm sure there's been better work since then.